Welcome back. This is the second video in our applications of exponential and logarithmic functions series. So exponential growth, and we talked about this in our first video, but we have for continuous growth, we have this new formula, a of t equals p times e to the rt. So that's my exponential growth formula if we are dealing with something that is compounded continuously. Okay, so when we're dealing with continuous populations, you can have money compounded continuously, and then you could deal with half-life or decay. We're going to use this formula. And one thing that we said is if we're talking about decay, we're talking about something decreasing, that we need to make sure we use the rate as a negative number. So that rate is going to be negative. And that's an important thing, otherwise you're going to end up with the opposite answer in your problem. Okay, so we have a doubling time or half-life shortcut. And we can only use this for problems that are dealing with continuous or exponential functions. We cannot use it for our interest compounded nthly, monthly, daily, quarterly, etc. So what we can say is that the growth or decay rate represented by the variable r and the doubling time or half-life are related by these two equations. So doubling time or half-life representing positive t. And you may say, well, Miss Stein, if we have to use a negative rate for decay, how come I'm not using the natural log of half for half-life? Because half-life is when something decays. Well, the reason that is, and you can check this in your calculator, but the natural log of 2 is equal to the same thing, but the absolute value of that natural log of 1/2. So you're going to get the same number. It's just natural log of 2 will be positive 0.69, I think, approximately. And natural log of 1/2 is going to be negative 0.69. So we can use this shortcut for both half-life and doubling time, since we can throw that negative rate out. Okay? But this would also be the same if you wrote that formula, r equals the natural log of 1/2 over t, or t equals the natural log of 1/2 over my negative rate. It's going to give you the exact same answer. So thinking back to our bunny rabbits and the doubling population, we had a formula, a of t equals 100 e to the 0.127 t. And the last part of that problem we did in the video prior to this, we said how long would it take for that initial population of 100 rabbits to double if they are increasing at a rate of 12.7% per day. And so we worked this out. We solved it as a long problem, but I just want to show you here we could use a shortcut. And if you were solving that, all you would need to do would say, well, that doubling time, it would take t, would be natural log of 2 divided by 0.127. And evaluating that in my calculator, I get the same number, 5.457851815. Okay, so we have that shortcut, and on that last problem we did, we could have used the shortcut. Just a reminder though, you can only use it for things that are increasing exponentially. Exponential growth, continuous growth, population growth, or decay. So let's do a word problem with half-life or doubling time. So here we have a problem. The half-life of carbon-14 is roughly 5,750 years. We want to determine the decay rate. And then we're using a little bit of science terminology. We're going to round to 2 significant digits. And you're not going to see that wording on your homework, but you may on a lab that we could do in class. So the half-life of carbon-14 is roughly 5,750 years. Find the decay rate. Well, we just learned that formula. That decay rate is going to be natural log of 2 divided by T. So the rate at which carbon-14 decays is natural log of 2 divided by 5,750. And if we type that in our calculator, we get 1.205473357 times 10 to the negative 4. So times 10 to the negative 4 means we take that decimal, move it 4 places to the left. Moving it 4 places to the left gives us 0.00012. So it went 1, 2, 3, 4. All right, and significant digits or significant figures, that's something we use when we have decimals that go on. And it's a way of rounding that lets us know where to stop. So we use it when we have a lot of zeros in front of a number, as we do here. So after those zeros, we have 2 significant digits, 1 and 2. So we're going to leave that as our decay rate. So my decay rate, R, is negative 0.00012. So what is half-life? You know, half-life is if we said we had some radioactive element, and say we started with 50 grams of it. If I told you the half-life was 10 years, then at year 0, we would have 50 grams. At year 10, though, we would have 25 grams, half of that. Year 20 would turn into 12.5 grams. 30, 6.25 grams. So what you see is this is decaying and it's losing half of its initial quantity every 10 years, every time that half-life passes. And so is this element, whatever it is it really ever going to go away? Because how many times can you cut something in half? And the answer is infinitely, right? I can cut this in half forever. It's just going to keep getting smaller and smaller and more microscopic. So in this regard, half-life can be used for carbon dating. So carbon-14 is in all living things, and it decays very slowly. So that's how when we pull some bones are too old, dinosaur bones are too old, but some prehistoric things out of the ground, we can determine how old they are. We use this half-life process. So let's look at a half-life example using carbon-14. So here we have a problem. Bones from a mastodon were discovered that had lost 77.2% of their carbon-14. If we use the rate we found on the previous problem, let's determine the age of the bones, and we're going to round to the nearest whole number. So we just talked about the decay rate of carbon-14. It has a half-life of 5,750 years, and the rate is 0.00012. And because this problem is dealing with decay, we're going to need to use a negative rate in the problem. Okay? So, half-life, anything that is decaying in this sense, is constantly decaying. continuously decaying, if you will. So we're going to use A of t equals PE to the RT. And if I take this formula and I set it up with my rate, that means I have A of t equals P e to the negative 0.00012 t. Okay, so now we have to figure out what we're being asked, right? We have bones from a mastodon. They've lost 77.2% of their carbon-14. We want to determine the age of the bones. We want to determine the age. So that means we need to determine the time. The age of the bones is how long they've been sitting in the ground. Essentially, you've got all of your carbon-14. You die, you immediately start decaying and losing that. So the only other number here we have is this 77.2%. So they have lost 77.2%. So at the moment when they are found, if they've lost 77.2%, how much do the bones currently have? And that would be 77.2 take away 100, which is 22.8%. So they currently, at the moment they're found, have 22.8% of the carbon-14. And how much carbon-14 did they initially have? Right at death, we had 100% of our carbon-14. So if I take these percentages and write them as decimal values, because we don't like to use percentages in the problem, that would be 0.228. And this one, 100 divided by 100 is 1. So I have an initial amount. We started with 100 and we've been losing carbon-14 to where we currently have 22.8%. So to set this up in the problem, we would say 22.8 or 0.228 equals 1 times E. And I really don't need to write that 1 in there, so I'm just going to say E to the negative 0.00012 t. So now I'm solving this exponential equation. I'm going to take the natural log of both sides. So the natural log of 0.228 equals the natural log of E to the negative 0.00012 t. And of course, what we notice here, natural log of E cancels each other out because natural log is base E. This is an exponential base E. And that argument in the exponent becomes the right side of our equation. So my last step would be to divide, and I've got the natural log of 0.228 divided by negative 0.00012. That's going to give me the time which these bones have been in the ground. And the time value that I end up with when I put that in my calculator is 12,320.08042. Or we could just say 12,320 years, which is a very old mastodon. So in this video, we've talked about our doubling or half-life formula for continuous or exponential growth application problems. And then we used that to determine a decay rate as well as the age of mastodon bones.